Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 25th, 2025, so just a few days ago. This paper introduces a model that achieves a decoding throughput 74% higher than a key competitor, DeepSeek v3, in a direct comparison. The paper is titled, Step-3 is Large Yet Affordable, Model System County Design for Cost-Effective Decoding, and as we'll see, it really pushes the boundaries for efficient, large-scale models. It proposes a novel approach combining a new attention mechanism with a specialized inference system to slash decoding costs. Alright, and the community's reaction online has been really swift. Researchers are buzzing about the technical report, specifically pointing to the clever hardware optimizations like multi-matrix factorization, attention and attention FFN disaggregation, which we'll get into. And, perhaps most excitingly for many, there's confirmation that Step-3 will be open-sourced on July 31st. This news has really generated a lot of positive discussion about making these powerful, efficient models more accessible. So, to really see what all the excitement is about, let's look at the data. This chart plots recent models based on two key metrics. On the bottom axis is the theoretical decoding cost, essentially how much it costs to run the model, where lower is better. On the vertical axis is activated parameters. For these large mixture of experts models, that's the number of parameters used for each token. You can see models like DeepSeek v3 and QN3 MoE forming an efficiency frontier. But then there's Step-3, the red star. It's way off to the left, showing a much lower cost. What's fascinating is that it achieves this while using more activated parameters than many others, creating a new, better trade-off. This really drives home the point that smart design is more important than just the parameter count. Okay, so what's under the hood of this impressive model? This table lays out the architecture. We see it's a massive 321 billion parameter model in total. But the key number here is the 38 billion activated parameters per token. This is achieved using a mixture of experts design, where the model intelligently selects small, specialized parts of itself to use for each task. It also features a novel attention mechanism called multi-matrix factorization attention, or MFA, which cuts down on both computation and the model's short-term memory needs. And that multi-matrix factorization attention design really shines when handling long inputs. These charts compare Step-3 against other hybrid models like Llama 4M and Minimax M1. On the left, we see the KV cache size, which is the model's short-term memory for text it's already processed. As the input text gets longer, Step-3's memory use, that solid green line, stays well below the others. This directly translates to the chart on the right, showing its theoretical decoding cost is also much lower, and that advantage just grows. And this cost advantage holds up in a broader comparison. These bar charts break down the theoretical decoding costs for Step-3 in cyan against its competitors. The left chart is for an 8,000 token context, while the right is for a much longer 32,000 token context. Across different hardware, Step-3 is consistently cheaper, but look at the far right at the setup labeled AFD. This stands for Attention FFN Disaggregation, a system that smartly splits the model's workload onto different, specialized hardware, which makes the whole process more efficient. Building on that idea of system efficiency, this next chart really visualizes why Step-3's attention design is so effective. It plots the compute required versus the memory access needed for different models. The dashed lines represent the ideal operating ratios, or rooflines, for various hardware chips. You can see DeepSeek v3 is very compute-heavy, while QN3 MoE is memory-heavy. Step-3, in red, strikes a balance. Its arithmetic intensity, which is just the ratio of calculations to memory needed, is a much better match for common hardware, allowing it to avoid major bottlenecks. So, how do they achieve this balance in practice? This diagram shows the system architecture behind it, called Attention FFN Disaggregation. You can see the process is split into two main parts. On the left, you have the attention instance, which handles the attention mechanism, and also has a router that decides which specialized expert to use. Then, that task gets sent over to the feed-forward network instance on the right, which is where the heavy expert compute happens. This decoupling is the key. It lets them run each part on different, optimized hardware, making the whole system incredibly efficient. So, to wrap things up, by combining that clever system design with a novel attention mechanism, Step-3 really shows that a model's cost isn't just about its size. This co-design approach sets a new standard, a new Pareto frontier, for balancing performance and affordability in large models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.